All right. So here it is. Here's problem number 3. This is probably the hardest one in the whole review. So we'll do this together and then I'll share it with you too. So we have y equals x squared e to the 1 over x squared. I have seen AP exams where they might have a combination of a polynomial with an exponential. And so the tactics that you learn on this are good. If I ask this, I might maybe not have a rational power here. I might have just a polynomial power. So I'd tone it down a little bit if I ask that on the test. So first thing I would do is go ahead and start by taking the first derivative of this thing. So we have y prime equals derivative of the first 2x e to the 1 over x squared plus derivative of the second, which is a match it case, e to the 1 over x squared, times the derivative of the power. Can you do the derivative of the power in your head there? Thinking of that as an x to the negative 2, would be negative 2x to the negative 3 power. That's correct. And then don't forget to finish off the product rule with an x squared. Okay, now this is a case in which I think it's best to clean it up and even factor out a GCF before you go to do the second derivative. I think that's probably the way I would go about it. So y prime is equal to, let's clean this up first, 2x e to the 1 over x squared. By the way, x cannot equal 0, so as I go and do some canceling, I can go ahead and do that, assuming that x is not 0. And then this would be minus, okay, this x to the negative 3, I would move that down to the bottom. It'd be x to the third on the bottom with an x to the second on the top. So that's going to end up just being a net gain, I guess, of x to the negative 1 is what it'll end up being. Or you could just add the powers here. So we have e to the 1 over x squared, x to the negative 1 power. The next thing I would do is go ahead and factor out. Am I missing the 2 here? Yeah. Nope, it stays up there. So we have a minus 2. Yeah, I got the minus sign and not the 2. Thank you. So put the 2 in there. So I have 2e to the 1 over x squared. That's that, and that. The x to the negative third and x to the second, simplified x to the negative 1, and I got my sign there. So I can factor out a common factor of 2, yeah, and e to the 1 over x squared. And that's a common tactic because what will happen here is this, when I use the zero product property, will have no solution. So when I set that equal to 0, there will be no solution for that. It is undefined at x equals 0. We need to keep that in mind because remember, when we break up our table, based on critical points, and critical points are where either where the derivative equals 0 or where the derivative does not exist. And so we still will have the potential for a break in our table there. So we have 2e to the 1 over x squared, and then I have left over x minus x to the negative 1. And that looks a little simpler, I think, than what I had up there. So if I set this equal to 0, we'll go ahead and take care of the first derivative at this point. Then by the zero product property, I can have 2e to the 1 over x squared equals 0, or x minus x to the negative 1 equals 0. Well, this over here has no solution. It has no solution. Although it is undefined at x equals 0, so we need to just note that. And then here, if we think of this as x minus 1 over x equals 0, it's kind of like what we've seen in this rate of change section. We have two terms. One of them's negative. I can move the other to the other side. So x equals 1 over x. And then solve this. Perhaps you could solve it by guess and check. But I have x squared equals 1 and x equals plus or minus 1. That's what I have so far. Now that's what the first derivative. So what are the things that can be answered with the first derivative only? Increasing and decreasing intervals, and then also extreme. So I can answer all that by just looking at our table for the first derivative. So how are we going to break up our table? It's going to look like. I am going to need to have a break at 0 because the original been defined at 0. So I need to have a break there. We're also seeing that in the derivative as well. So my table is going to look like this. I have a sine of f prime, and then I have my interval here. And we're going to go from is there anything else in my domain I need to consider up here? Looks like just x cannot equal 0. Am I missing anything else? We could graph it to see. I don't think so, though. So we're going to go from negative infinity up to, looks like -1, and then -1 to 0, and then 0 to 1, one more, 1 to infinity. So those are my intervals. I'm going to check the sign of f prime there. So I'm back up to y prime. I think I would use this version of y prime. Let's go ahead and kind of break this up a little bit here and see what we can figure out. If I plug in, say, for example, a -2, what's going to happen when I plug in a -2? What's the sign going to be? I don't care what the value is, but can you figure out what the sign is going to be just looking at it? Plug in a -2 here. It's going to just get squared, so it's going to be e to the 1/4. Which is positive, times 2, which is still positive. Plug in my -2 here, that's going to be -2 minus 1 over -2. So it'll be -2 minus 1 over -2. So -2 plus 1/2. So that's going to be a negative number here. So it looks like when I plug in -2, I'm getting negative. Yeah. Now don't. So don't assume this is going to act like a polynomial. It's not going to alternate necessarily. If I plug in something between -1 and 0, kind of limited. That's a bummer. I got to plug in something like 1/2. But if I plug in 1/2 here, this whole term is going to be positive. So just keep that in mind. If I plug in 1/2 here, I have 1/2 minus 1 over 1/2, or 1/2 minus 2. That'll be negative again. So there's not a sign change there. What about at 0? Between 0 and 1/2, if I plug in positive 1/2 here, this will still be positive. 1/2 minus, well, this was a negative 1/2 though. Let's see, 1/2 minus, so did we mess that up? Okay, this is 1/2 minus negative 1/2. Sorry, so this is negative, so this does, it does end up being a positive. Because we were plugging in a negative 1/2 here. So negative 1/2 minus, negative 1/2 minus, no, it's negative 1/2 minus a -2, so it's going to be +2. So it does end up being positive, so that's positive. That's negative. And then from 1 to infinity, if I plug in something like 2, what happens there? This will be positive again. 2 minus 1 over 2 will be positive, so it goes back to positive. So that's it. So checking our intervals, it does end up alternating, but it doesn't have to, unless it's a polynomial. A certain polynomial as well. So how do I interpret this then? Going back to f. F is increasing on -1 to 0, and I could close off -1. In the textbook they close it off if it's in the domain of the original. I can't close off 0, because 0 is not in the domain of the original. Union 1 to infinity. And f is decreasing on negative infinity to negative 1, and I could close off negative 1 because that is in the domain of the original. And then also union open interval 0 to 1. So those are my increasing and decreasing intervals for this function. I'm going to be a little bit careful with my maxes and mins. Because on my first derivative test, I see that f is decreasing from here to negative 1 and then changes to increasing. I can see that x equals negative 1 is a local or relative min. So x equals negative 1 is a relative min. Now, at x equals 0, it looks like it could be a max, but it's not because 0 is not in the domain of the original. So although we have the sign change here, 0 is not a max. And then here, x equals 1 is a local min as well. So that gives us increasing, decreasing, and our min. And unless it came up, so what's happening at x equals 0? What type of feature do we have? Maybe a hole. Is it going to be a hole or an asymptote? You can check it by, now it's a hole if it could be factored out. So, and then it's an asymptote otherwise. So you should see an asymptote there. And this is, it always gives me this message when I'm trying to record, and then my recording doesn't work. I don't know what to do. All right. Now, let's go back up here and take the second derivative. So let's start with y prime equals 2e to the 1 over x squared times x minus x to the negative 1. We're just going to start with that. We'll copy down a different color here. So y prime equals 2e to the 1 over x squared times x minus x to the negative 1. You want to hang out and see the end of this one? I'll finish it now. So second derivative. Derivative of the first is 2e to the 1 over x squared
Thin bar day. Please report to the attendance
negative
office.
2x to the negative 3 times the first
Report to the attendance office.
plus derivative of the second. So derivative of this thing is going to be 1 plus x to the negative 2 times the first, 2e to the 1 over x squared. So derivative of the first is this times the second plus derivative of the second is this times the first. And that can be cleaned up, factored out, and then set equal to 0. Algebra like nothing you've ever seen before. So we have, let's see here. Could take this negative 2 and this and put those two together, it looks like. So that would be negative e to the 1 over x squared. And then if I distribute this x to the negative 3 out, I get x to the negative 3 plus 1, or x to the negative 2 power. And I moved that negative out already, so the negative is taken care of. X to the negative 3 times x to the negative 1 would be minus x to the, add the powers, negative 4 power. And then plus 2e to the 1 over x squared times 1 plus x to the negative 2. Negative 2, this should be a negative 4 here. So 2 times 2 is 4. So it should be negative 4 e to the 1 over x squared. And then what's left over is this. x to the negative second minus x to the negative fourth. And then here, I just left it as is, just changed the order. But I'm looking at this like I could probably factor out a 2e to the 1 over x squared like we did in the previous one. So if I factor out a 2e to the 1 over x squared, I'm left with negative 4
Please have the following students come to the main office.
x to the negative
Joseph
2
Davis,
plus 4
Sydney
x to the
Davis,
negative 4.
Caitlin Miller. Please
Plus-
come to the main office.
This will just be a 1 plus x to the negative 2.
It's negative 2.
Is it negative 2? Where?
No, down. You took it a 2, so.
We got a 2. Yep, should be 2's. Thank you. And then if I took out a 2 here, I should have my 1 and my x. And then we could combine these two terms. So this would be it for our second derivative. 2e to the 1 over x squared. And then I have 2x to the negative 2 plus x to the negative 2 would give me 3x. Did I have the right sign in here?
It should be negative.
It should be a negative. Say. Okay, let's see. I have a negative sign here, so if I pull out a positive 2e to the 1 over x squared, this would be a negative 2x to the negative 2, and then this should be a positive 2x to the negative 4. My sign's good here. It depends if I pull out a 2 or negative 2. I maybe should have pulled out a negative 2. No, I don't know which would be easier. It's not going to matter too much. So now I have, looks like these two, if you put these two together, start with the 2, start with the 1, and then we'd have minus x to the negative 2, there's just one of them, plus 2x to the negative 4. If we go with decreasing order of the powers, actually my highest power is x to the 0, right? So there it is. And I'd set that equal to 0. And then by the 0 product property, I have 2e to the 1 over x squared equals 0, or 1 minus x to the negative 2 plus 2x to the negative 4 equals 0. Now, there are a couple ways to approach this. You could actually, believe it or not, use the quadratic formula on this. You could. It's of that form. You would be solving for x to the negative 2. Instead of having x, it would be x to the negative 2. What you would discover if you went about it with the quadratic formula is that you get a negative under the radical, which means no real solution. Probably the way I would approach this in a calculator-based portion, which this would be
Miss
on there,
Angona,
is you would
please
graph
turn to
this
the counseling
and
office.
see that it never crosses the x-axis.
Shannon
Same thing
Angona,
with this. So
please
there's no
turn to the counseling
solution
office.
here, no solution here. But we do know, oh boy, this is just, but we do know that x equals 0 is where the second derivative does not exist. Okay, so x equals 0 is where y double prime does not exist. So we still need to break up our table into two intervals. Okay, it's going to go from, this is the interval here. This is sine of f double prime or y double prime. It's going to go from negative infinity to 0, and then 0 to infinity. And we're going to plug in values, probably negative 1 and 1, to my second derivative up here and see what happens. And then I can talk about concavity. Now, point of inflection, it's not going to have one. Why not? Yeah, well, there may be a change. There could be a minus and a plus here, but at the change, it's not defined in the original. So it won't have a plane inflection. So if I plug in -1 here, oh boy, here we go. Some arithmetic up here. If I plug in -1 here, would you agree this will be positive? So let's see if we can work through the -1 with the right sign. Here we go. Help me out here. 1 minus 1 over -1 squared, so that would be 1 minus 1, right? That would be 0. Plus 2 over -1 to the 4th, which would be 2. So I think that's positive. And that was with the -1 plugged in. And then from 0 to infinity, if I plug 1 in, what will change there? I'll get 1 minus 1 is 0. Nothing. Huh? So I get plus and plus here, meaning what? What's that? It's always concave up, yeah. Always concave up. So if I were to do an interval, I would say it's from -infinity to 0, union 0 to infinity. Why would I include that union here if I'm talking about concavity? Yeah, it's not defined at 0, so you could say it's always concave up, and then maybe in words say it's not defined at x equals 0, but it's always concave up. There's no point of inflection. And then I would graph it and make sure everything agrees. But that looks familiar in terms of what they were for. So you got it done.